New in version 24 is the cable element, now available in two different formulations. With the classic Ernst formulation, which is widely used in design, LUSAS automatically adjusts the cable's effective modulus of elasticity based on the tension experienced by the cable. When this formulation is selected, the number of divisions is automatically set to 1. With the catenary formulation, you can obtain a more accurate representation of cable behavior, making it especially suitable for nonlinear and time history analysis. Although you can use as few as a single element, since LUSAS will automatically discretize the cable, a larger number of elements provides a more refined estimation of relative cable displacements, a topic I will revisit later in this video. In this example, we are looking at a simple cable mast, where a single pylon is supported by 3 cables. When using cable elements, defining cable shape attributes is required. Several options are available: total length, sag, initial tension, and target tension. In this example, I have specified an initial sag of 0.3 meters, measured vertically. For more details on these options, simply click the Help button. The structure is subjected to gravity loads in the first load case, where manual nonlinear controls are applied. In the second load case, a wind load is applied to the pylon. Here, automatic nonlinear controls are used with small load increments to accurately capture the nonlinear response. Once the analysis is complete, several results can be examined. First, we can look at the deformed shape. We can observe that 2 of the 3 cables are experiencing relatively large deflections. Actually, let's go to the final stage of the analysis, of course. 2 of these cables undergo relatively large deflections. As the wind acts on the mast, the pretension in these cables decreases, causing them to become progressively more flexible. The third cable, the critical cable, behaves differently. Its pretension increases, causing its shape to move closer to the initial straight chord defined by its endpoints. This is, of course, as expected. Using the charts facility in LUSAS, we can examine the load displacement response at the top node of the mast. Initially, the structure is highly flexible as some slack is present in the cables. As the cables progressively engage, especially the critical one, the overall structural stiffness increases. We can also examine the tension in each cable. The critical cable, the one experiencing increasing tension as the wind load rises, shows a strong increase in tension. Conversely, the other 2 cables experience a reduction in tension, which is highly nonlinear. We can also plot the absolute displacement of the midpoint node of the critical cable, which is this node here. As expected, the initial displacement is 0.3 meters, corresponding to the sag assigned to the cable. The initially soft portion of the curve is followed by a much steeper response. This occurs because as the cable tension increases, the sag is progressively relieved and the cable shape approaches the straight chord defined by its 2 endpoints. A new result entity introduced in version 24 is the relative cable displacement. This quantity represents the displacements of the cable relative to its initial sagged configuration. It should not be confused with the more familiar absolute displacement result. This slide summarizes both concepts. The table on the left lists the initial position of the midpoint node of the critical cable, its sagged position, and its final position under the applied wind load. The absolute displacement, shown in the contour plot as 242 millimeters, is consistent with the values reported in the first 3 rows of the table. This is very simple math. Similarly, the relative displacement shown in the contour plot as 151 millimeters also matches the nodal positions reported in the first 3 rows. This concludes this short video on the catenary formulation of the cable element in version 24. Stay tuned for more content on this topic. Thank you.